Begin our second session of today, and we will be kicking it off with Ted Johnson from the University College London, who's going to be talking to us about wave packets in the anomalous Ostrovsky equation. So thanks for giving a talk, Ted. Fantastic to hear from you again. The floor is all yours.
Thanks, Dan, and thank you for the organisers. So I just want to talk today about a very simple problem. It's an example of using Whitham modulation theory, and it has the advantage that the Whitham modulation theory is reasonably straightforward, and it lets you work out what's going on in the fully nonlinear equation, so you don't have to search for solutions. The particular solutions I'm going to talk about are wave packet solutions, and by that I just mean somewhere where there's a rapidly varying packet of waves, of course, and it's embedded in a smoothly varying outer solution, and I'll demand that it's isolated in the sense that the outer solution goes to zero at infinity. This is a solution we'll come to later on. The red curve, which exists everywhere, is the Whitham modulation theory, and the black curve, which has been superposed on the red curve, is the solution to the full equations. Okay. So what's the equation we're going to consider? It's the Ostrovsky equation. It arises for weakly nonlinear, weakly dispersive, and weakly rotating waves. So here's our x momentum equation with the Coriolis term on the right-hand side, the y momentum equation, again with the Coriolis term on the right-hand side. And epsilon here will be small most of the time. It's the strength of the rotation, but right at the end, we'll comment on what happens for large epsilon. These equations are normally combined. They're combined by Ostrovsky and called the Ostrovsky equation. And then you can see that it's a non-local equation because we have the KdV operator here. And if we take the x over to here, we have an integral operator on the right-hand side. This parameter gamma that appears here is just a sign parameter. If there's no vertical shear in your flow, then gamma is +1 and it tends to be called normal dispersion. But Roger and Karima have shown with Alias that if there is vertical dispersion, vertical shear, then gamma can be -1. And similarly, Yuri and Obregon have shown that gamma can be negative for magnetoacoustic waves. So how does Whitham modulation theory work for this? Well, very standard. We introduce long x and t scales. And of course, you know that we could use multiple scales to get these equations. But today I'll just go quickly through using the averaging operator because we can then see what the equations mean physically. So here's averaging the x momentum equation, averaging the y momentum equation, and then just by differentiating, we put them together and we get the first of our equations, the first averaged equation. And really, this is just an equation for conservation of mass. We can get another equation, as is usual. We multiply the x momentum equation by u, and really it gives us a momentum flux equation. So this is the momentum flux equation. And now we can integrate that equation, we can average that equation. Here's the average of that equation. Use the second equation, and we now get our second governing averaged equation. So we've got two averaged equations, one which is really from conservation of mass, and one which is really from conservation of x momentum. We can get a third equation, and that closes our system, as we'll see, because we only have three unknowns. And we get our third equation. It's the standard equation, of course. It's the conservation of crests, and it just says that the wave density, it travels with the phase speed. The wave density is the wave number, so we get our conservation of crests equations. So there are our three equations. Why is 3 enough? Well, I'm sure you know that the KdV can be represented in the three Riemann constants or Riemann variables that introduced by Whitham. We'll call them R1, R2, and R3. The solutions we look at today are the conoidal solutions. The KdV, of course, is the limit of the problem we're looking at when epsilon is identically 0. So here is the conoidal solution, and all the parameters that you see in the conoidal solution are simply functions of the R's. So it sits on a constant shelf, U min. It has amplitude A. It has period K, which is the complete elliptic function. It has wave number little k. It has phase speed c. And theta is some arbitrary translational phase. One thing we'll need later on is the mean value, and here's the mean value down here, denoted by D, the average value of U. And like everything else for the KdV, it can be expressed just in terms of the R's. So we have three unknowns, of course, R1, R2, and R3, and we have three governing equations, and that's the Whitham system, of course. So we just follow Whitham, and we do exactly what Whitham did, and we get exactly his equations. The only difference is that there is an inhomogeneity on the right-hand side of his equations. This capital D, the derivative of capital D is the average. So capital D is the integral of the average value of U. And the speeds that appear here, of course, are precisely Whitham speeds. So this looks very much like the Whitham system, but just with an inhomogeneity. Well, the types of solutions we'll look at will be for packet solutions where the envelope propagates at some constant speed s. So we introduce some x prime, which x minus st, write everything out in terms of x prime, drop the prime, and we get this set of ODEs. This is the Whitham solution, and we get our fourth ODE, which defines capital D. Now for these packets, normally C, the phase speed, will vary across the packet, but solutions have been found for anomalous dispersion, and we'll confine attention to anomalous dispersion now, when the packets are steadily propagating isolated solutions which are steady in a frame moving at speed c. And some were found by Urey and Obregon, and some were found by Ashley Whitfield. So we'll look for cases where S is the same as C, and that is a constant across the packet. You probably know that if we demand that for linear waves, that the group velocity and the phase velocity coincide, that occurs at an extremum of the phase velocity. Okay, so what's the problem we're going to do? Well, we're looking for wave packets. We're going to suppose that they're in a region with bounded by x edge, x sub e, and for mod x less than x sub e, we have this rapidly vary solution, and for mod x greater than x sub e, we have a decaying solution that vanishes at large x. Now, for the inner solution, where things are varying rapidly to match smoothly to the outer solution, we need that the derivative of the inner solution, the gradient of the inner solution, will vanish at these edges. So that gives us a condition on our problem. Moreover, the solutions that have been found have positive mass in the inner solution. But integrating the Ostrovsky equation shows that the total mass has to be 0. So that means that the outer solution must be negative at the edges of the envelope. And therefore, that means that the packets must terminate in minima of the conoidal solutions. So we know that there must be minima of the conoidal solutions at the edges of the packets. If we want a symmetric packet with a central maximum, that means that the number of wavelengths is odd. If you want a symmetric packet with a central minimum, or a local minimum at the center, then n is even. So in a way, we've now got an eigenvalue problem. We get the ones with the central maximum by choosing the phase to be 0, and we get the ones with the central minimum by choosing the phase to be the half period, k. And our eigenvalue relation is the total change in the phase moving across the group. So moving from one end, the left-hand end, to the right-hand end, the total change in phase, which we can say is the integral of its derivative across the packet, which is, of course, the derivative is just the wave number. So the integral of the wave number across the packet must be our integer n. So this is an eigenvalue problem for our for these packets. What we're saying is that for a given epsilon, there exists only a discrete set of solutions. So it's a nonlinear eigenvalue problem. As we'll see later, formally this is valid, of course, only for epsilon goes to 0 and n goes to infinity, with the total change in phase finite. But we'll see it stays good for right down to n equals 1. Now, if we were doing this for the full problem, we would have to stop here and we would have to solve a nonlinear eigenvalue problem by some form of searching method or some form of continuation method. But the Whitham system has the property that it depends continuously and smoothly on the phase speed c. So what we can do is we can solve at every c by integrating the packet equation or the Whitham equations from the origin outwards to when the packet ends. The packet ends when two of the Riemann variables coalesce, when two of the Riemann variables collide. And that will tell us the end of the packet, xe is a function of c, and it will tell us the total phase change over the packet is a function of c. But this function we're going to end up with is a monotone decreasing function. And so we can invert it to give c as a function of the phase change. But that isn't precisely, of course, just epsilon n over 2 from our eigenvalue relation. So if we're given a value of the rotation, epsilon, and we want a packet with a certain number of wavelengths in it, we can compute this quantity, epsilon n over 2, and then we just look up c. That tells us what the corresponding c is, and then we just do the integration, and we know what the corresponding solution is. So we've avoided having to actually solve an eigenvalue problem. The only technical difficulty is that if we're starting off at the origin, we need to know the boundary conditions on the Riemann variables at the origin. How do we find those? Well, one of them comes from normalizing the packet envelope to have amplitude unity at the origin, and the others come from applying conservation relations which we can derive, which hold across the packet. And if we do that, we get an explicit formula for R1, and if C is positive, it's very easy. We get explicit easy formulas for R2 and R3. If C is negative, there's a bit more work, but we can still get explicit formulas for the R1s. So our problem has been parameterized, in fact, by the phase speed C. So what do we do is integrate this numerically. There's another technical issue. The Riemann variables at the end of the packet will collide. R2 and R3 will coalesce, giving us actually a solitary wave at the end. So that means that the gradient R2x and R3x will become infinite. That'll lead to, well, that would be an inefficient way of integrating then, but we can get around that. The standard way of getting around that is to introduce an arc length variable, tor, and to integrate along one of these with the arc length variable. So we'll integrate along R2 using an arc length variable, and then there's no problem. There is no infinite gradient. So just to summarize what system we've got, here are our three Whitham equations in terms of the variable torr. We have the average equation in terms of torr, and we can keep track of the rate of change of the phase in terms of torr and the rate of change of position in terms of torr. So we have 6 ODEs to integrate, and we have initial conditions for those, and we just integrate those equations until the two of the Riemann variables coalesce. And in fact, then we can continue integrating outside into the slowly varying outer region. And here's a typical solution. Here's a typical solution. Here is the XE is the end of our packet. This is for C equals minus 0.05. R2 and R3 coalesce at XE with this infinite gradient. That's the end of our packet. It ends in a solitary wave. R1 is slowly varying and moves through the packet. And here's D, which again is our slowly varying average, which moves through the packet. So this is one solution. We can now run this for all the values of C, and we get these two graphs. This is the width of the packet as a function of C. It vanishes at C equals a third. And this is the change of phase across the packet, again, as a function of C. At C equals a third, in fact, you could show the solutions a train of KdV solitary waves of amplitude 1 on a vanishing shelf. Now, as we said, this equation, this relationship is monotonic decreasing, so it can be inverted. In other words, if we know a value of epsilon and n, that will tell us theta sub e. We then go across and we can then read off the relevant value of C, and therefore we know what Riemann system to run to simulate our flow. And here are some of the results. This is across the bottom here is the rotation rate epsilon. Going up here is the speed c, and the dashed lines are the solutions of the Whitham system. So this is n equals 1, 2, 3, 5, and 7. The solid lines are solutions of the full Ostrovsky equation. So this, as we expect for small epsilon, they coincide with the Whitham modulation theory. And as epsilon increases, as we increase the rotation rate, they slowly move away from the Whitham theory. One of the interesting things about these full solutions is that they terminate. In other words, if we follow a set of any one of these solution curves, eventually it terminates, and it terminates at these open circles. So these are the termination points of these. And we can give a very simple argument for what's going on at the termination. Of course, if we look for a lower bound on the speed, then we can just say, all we've done is insisted that the packets join smoothly to the outer solution. We haven't put any condition that the packets decay, that the outer solution decays at infinity. Now for C positive, all outer solutions will decay, so that's not a problem. But with C negative, then we could have coexisting linear waves. And if we look for the coexisting linear waves, we find that to exclude coexisting linear waves, we must take C bigger than minus 2 epsilon. And that's what this line is. This is the line down in this region here. There are coexisting linear waves. So there may be isolated packet solutions, but this solution won't be, there won't be a continuous system of packet solutions through here. The other thing to look at is the fact that the n equals 1 wave is anomalous in that this curve does not terminate. And in fact, we can extend this to arbitrarily large epsilon. And here it is, it's extended to arbitrarily large epsilon. And it goes closer and closer to the linear system. And in fact, you could show that the large amplitude, the large strong rotation solutions of the Ostrovsky equation correspond to the weakly nonlinear solutions. And in fact, then once we're in the weakly nonlinear case, of course, we can make an NLS model. Just here are some pictures of some packets. There's a packet with 7, 4, and 2 wavelengths inside it. These are all plotted at the open circles for their branch. So this is the maximum possible error that you can get between the Whitham modulation theory and the full equations. And you could see that as the number of peaks, the number of wavelengths decreases, then long dispersive waves in the outer solution mean that really we should go to higher order in the outer solution. But it's still highly accurate in getting the correct shape of the inner solution. Oh, and now comment on the NLS solution. We just turn the handle of the usual NLS calculations on the nonlinear Ostrovsky equation. And as always, you get the second order term free. That's very important because that gives the up-down asymmetry in the problem. And the phase speed and the group speed appear here, and they've been computed by Roger and Yuri and Alias. And if we use those, we get a packet solution here using the NLS. So for large epsilon, this is epsilon equals 0.8. And here is the packet solution. The red is the NLS solution, the second order NLS, and the black is the full Ostrovsky solution. And notice you do need the second order term because this is significantly not symmetric up-down. The maximum is normalized to 1, but the minimum here is about minus 0.6. So the second order term is significant in this. Finally, we can look at when C is negative, then there is a point x0 in the outer region, where both the gradient of the outer solution vanishes and the total mass over the enclosed region vanishes. So that means that we can just reflect the solution about that point. We can extend the solution to be periodic with period 2x0, and that the mass will vary over each period, and that satisfies the Ostrovsky zero mass constraint. So we can construct, by reflection, we can construct periodic solutions when C is negative. In fact, they're going to be very good because the solution of the WMT of the modulation equations actually is an exact solution of the outer equations. So here's a wave train consisting of a train of n equals 3 wave packets, and then this inverted parabola is the outer solution, and this has a speed of minus 0.1, and in this case x0 or 2x0 is 5.2. So again, the red solution is the modulation solution, and the black solution is the solution to the full equations. And some final comments then. The solution of the, we know that the solution of the reduced Ostrovsky equation will break if at any time u double dashed is less than minus a third, and it won't break if for any initial conditions where u double dashed is greater than minus a third. So what we also know is that these solutions for C less than 0 that we've been discussing, they actually lie exactly in the outer solutions on U double dash equals minus a third. So what that seems to be saying is that if you look at the evolution of solutions of the full equations, then the packets are associated with breaking of these long wave equations. So at the instant of breaking, they break and they give us these packets. Certainly for the ones that we constructed there, it seems that they are stable. If you use those as initial conditions for numerical integrations, then they will remain solutions of the equations. They won't break down. And finally, just a comment that you won't see the higher order ones if you simply take a very large single hump of fluid, a large narrow single hump, and let it evolve. It would evolve into under the usual KdV evolution into a set of solitary waves, and then each of these solitary waves would evolve into an n equals 1 soliton. And finally, just to say that the details of some of this can be found in this PhysRef paper. Great, thank you.
Thank you very much, Ted. Really amazing talk, actually. So if we've got any questions for Ted, either feel free to unmute yourself and ask him directly or put them in the chat. I actually had one you've started to partially answer in terms of stability. So far the work has just sort of had a numerical kind of implication for stability, the fact that they stick around when integrated for a long time. Have you had a look at the analytical approach to that?
Not at all, no. So no, I have no idea. In fact, I'm not entirely sure how you'd approach it.
Yeah, because I'd imagine it gets quite a complicated
I guess
calculation.
that's right. If you might be able to. No, at this stage, yes, I'm not sure how one would do it for the full, certainly for the full equations. Maybe you can do it, use the approximate solutions in some way.
Yeah.
Oh.
Yeah, thank you.
If
Yes.
Can I ask? So it looks, if you go a certain number of slides back where there is a fourth order ODE with a small parameter, I think, yeah, that one. And so I was wondering, one can, if you have ever considered such thing as called embedded eigenvalues for
No,
that.
I think that's a good question. No, that you're quite exactly right. That if I can even go back further, what happens here numerically is I find these solutions by continuation, and at this stage there are no more solutions. The procedure doesn't converge, but you're quite right. Somewhere down in this region here, there could well be isolated packet solutions, or they could be generalized. And in fact, I'm certain there are some generalized solutions. You can almost see this trying to, where is it? You can almost see this trying to go to a generalized solution. I think if this is the last of the converging solutions, but the last of the decaying solutions, but I think you could probably get this to become a generalized wave packet.
I would have some, possibly some, at least idea of some approach.
Oh,
and
good. I'm not sure who I'm talking to, but I'd be delighted if you got in touch with me.
I'm Alexander Tovbis, and we met on many.
Absolutely.
many.
I just don't. I can't see your face, and I didn't recognize your voice. I'm sorry. Yes, I'd be delighted if you wanted to get in touch.
It's morning, Ted. It's morning here, so my voice may be hoarse, or I don't know.
If you would get in touch, please
like
do so. It'd be something I'd be very interested in.
Okay, I would be happy because I have years ago a paper with Dmitry Pelinovsky where we considered fifth order perturbed KdV and made traveling wave for fifth order perturbed KdV and made similar analysis.
Absolutely, yes. It's remarkable how much of the things you see here are in the fifth order KdV. They're very, very similar.
Mhm.
Okay, okay. I can send you the paper certainly.
Oh, please do. Yeah.
And we'll be happy to discuss.
Please. Yeah.
Thank you.
Awesome. I think we've got to wrap up questions for now, but I imagine, Ted, you'll be around during the break if
Yeah, of course.
anyone's got any
Yeah.
further questions.
Yeah.
Wonderful.
I'll press stop share, I guess.
Yep. Yeah, and thank you again for your talk. Really enjoyed it.